So, hello everyone again. This is lecture number 4 part 1 of alternating current. In the previous lecture we have started with the discussion regarding the AC voltage applied to a series RLC circuit LCR circuit, and we have completed regarding what are the basically two different types of solutions. The first was your phasor diagram solution, the second was your analytical solution. We understood basically that why we moved on from phasor diagram solution to analytical solution. So, basically what was the difference between them, how at the end we got the same answer only. So, our phasor diagram solution gave us the steady state solution, but the analytical solution gave us the full general solution. Okay. That thing being said, I did a small introduction regarding the resonance concept which we need to understand, because major part of the topic here which we need to understand is resonance only. One is resonance, one was RLC circuit, and finally the most important thing are application part. First is your power factor and second is your transformers. So, that thing being said, let us start with the discussion regarding resonance only. I will again start just because a little introduction was only being done, then we will move on to the application of this resonance, the understanding of resonance, mathematical part and so on. So, this is lecture number 4 part 1 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, a course outline for you. First of all, currently we are on the 6th topic, that is AC voltage applied to a series LCR circuit. Okay. Before this we have completed with the introduction part. In introduction part we basically understood as in what is DC source, what happens in the DC voltage, what happens in the DC current, how are they different from or how are they as comparison with AC source, AC voltage and AC current, why AC source or AC voltage is being said advantageous or more better for transmission of voltage from let us say point A to point B which are very far from each other and so on. In the second concept regarding AC voltage, we started with the discussion as in what happens when only a single resistor is being applied or a single resistor is being used. So, basically an AC source was being used and then a resistor was being applied, and using the voltage assumption that let us suppose that V is equal to Vm sin omega t, we got the value of current. The value of current obtained was nothing but I is equal to Im sin omega t, where Im is equal to Vm upon R. Then we understood a new concept which was basically phasor diagrams. So, phasor diagram is a simple concept in which the complete waveform is being divided or being converted into some sort of circular nature, in which the arrows denote the vector, and it basically moves in the anti-clockwise sense, and that is how we can understand this complete concept of waveform in the circular vector nature. So, as it is not so significant for the resistor part, but it is very significant as far as AC voltage applied to inductor and capacitor, and basically LCR circuit is being understood. So, understanding after this phasor diagram, we understood about AC voltage applied to an inductor, in which we basically got that if V is equal to Vm sin omega t, what is the value of current being obtained, and next was similarly regarding AC voltage applied to a capacitor. After the individual senses were being understood, we understood about the 6th topic, that is AC voltage applied to a series LCR circuit, in which we basically calculated or defined a new terminology which is called as impedance, that is Z, which is nothing but equal to under root of R square plus XC minus XL whole square. So, that is nothing but analogous to resistance being offered by the AC circuit, and we basically understood how it is being implemented in both phasor diagram solution and analytical solution. So, that is what was being completed till now in all the 3 lectures. Now, in this 4th lecture, let us start with the discussion regarding resonance. So, this was the analytical solution I explained to you in the last class only. So, finally, after assuming a solution of q is equal to qm sin omega t plus theta, we finally obtained that current obtained is nothing but equal to Im sin omega t plus phi, correct, where what is Im is basically Vm upon Z, and what is phi is basically equal to tan inverse of Xc minus XL upon R. Please remember, here Z is nothing but equal to root over R square plus Xc minus XL whole square. Okay. So, that is how we understand this impedance concept. That thing being said, now let us move on again to the recent part which we have concluded in the last class. Just an introduction was being done, that is resonance. Okay. So, basically what is resonance? Resonance is basically the increase in the amplitude of the of the concept or the series circuit which you are talking about, when the frequency being obtained is very close to the natural frequency. If we say that the natural frequency is denoted by omega naught, then if the frequency of the circuit is very close to omega naught, then the amount of amplitude being obtained is at a much higher value. That is just the simple layman language of how we can understand resonance. So, I guess these all things were basically understood in the last class only. Let us move forward with the mathematical concepts regarding all these things. Fine. So, now let us understand the same thing for an RLC circuit. So, for an RLC circuit, so either you can say LCR, you can say RLC, you can say CRL, everything is same only. It basically means that everything is connected in a single circuit. One is R, that is resistor, L is inductor, C is capacitor. Okay. So, for a RLC circuit driven with voltage of amplitude Vm and frequency omega, we found that the current amplitude is given by what? So, basically current amplitude is nothing but I is equal to Im. Please understand this concept very clearly. So, Im is nothing but equal to Vm by Z. Every time for an RLC circuit we just obtained that Im is what? Im is nothing but Vm upon capital Z. Writing the complete value of Z, I just revised, it was nothing but under root over R square plus Xc minus XL whole square. It is Xc minus XL whole square. Okay. Now, just a quick revision. What is Xc and XL here? So, Xc is nothing but equal to 1 upon omega c. Please remember, Xc is capacitive reactance and it is 1 upon omega c, not omega c. Sometimes students do confuse about this concept. Please remember, Xc is 1 upon omega c and not omega c, and XL is nothing but product of omega and L, where L is the self inductance of the inductor. Okay. So, now please try to understand that if I try to vary omega, if I try to vary this value of omega, there may be a particular value, such that, let me write. So, if we try to vary omega, there will be a particular value of omega such that such that 1 upon omega c is nothing but equal to omega L. There will be a such particular value such that 1 upon omega c is equal to omega L. If you try to do mathematical analysis more here, we will get omega square is nothing but equal to 1 upon LC, 1 upon LC, or we can write omega is nothing but equal to 1 upon root over LC, correct. So, this value of omega is nothing but this value of omega is denoted by omega naught. Okay. So, this value is denoted by omega naught, and this is only called as your resonant frequency. Now, question arises, why this frequency is called as resonant frequency? Let us go by the wording. It is said that it is sort of a frequency which is resonant, as in it is providing you with the phenomena of resonance. What was the basic layman understanding of resonance? The basic layman understanding of resonance was that if we try to provide a value of omega which is very close to omega naught, we will get the amplitude value much higher. Let us try to understand this here only. Let us say if that value of omega naught is being used here. If that value of omega naught is being used here, that means what is Xc is equal to XL, correct. So, because this is only written here. Now, if Xc is equal to XL, let us try to write the value of Im here. So, if Xc is equal to XL, that means what? Omega is equal to omega naught, correct, because that is only we are calculating here. From Xc is equal to XL we went here, and finally we got the value of omega which is equal to 1 upon root LC, and we are denoting this omega is nothing but equal to omega naught. So, if XC is equal to XL, what is omega? Omega is equal to omega naught, and at that point what is the value of Im? Im is nothing but equal to Vm by capital Z, which is nothing but equal to Vm upon root over R square plus Xc minus XL whole square, correct. As we know that Xc is equal to XL, therefore Xc minus XL will be equal to 0, and therefore it is quite clear that Vm upon R is being obtained. Now, if you look at this very clearly, the value of Z being obtained when Xc is equal to XL is the minimum value which we can obtain for impedance. If Z minimum is being obtained, then it is very clear that the amount of current being produced is maximum. I will write here. So, if Z is equal to Z minimum, that simply means that I m is nothing but I m max, correct, and that is the only concept of resonance which we require, right. What is the basic concept of resonance? The basic concept of resonance says that if the device frequency is such that it is very close to omega naught, or it is close to omega naught in mathematical part, then the value of current obtained is maximum. So, mathematically also we got that for value of omega which is equal to omega naught, we got the value of Im which is maximum. So, this is the basic concept of resonant frequency. So, please remember this value of resonant frequency, this may be asked directly in exams. So, omega naught value is for RLC, please remember it is only and only for RLC circuit. So, for an RLC circuit, the value of resonant frequency which is denoted by omega naught is equal to 1 upon root LC, okay. Fine. So, that was the concept here. Now, let us try to understand more here. So, at resonant frequency what will happen? It will happen that the current amplitude is maximum, that is Im is equal to Vm upon capital R, okay. So, I just derived the value of Im is nothing but equal to Vm upon capital R. So, figure shows a variation of Im with omega in an RLC circuit with L is equal to 1 millihenry, C is equal to 1 nanofarad for two values of capital R. So, first is for R is equal to 100 ohms and second is for R is equal to 200 ohms. So, let us suppose now we are trying to understand this concept. So, let us suppose we have L is equal to 1 millihenry, C is equal to 1 nanofarad and resistance is 100 ohms and 200 ohms. It is quite clear that with the increase in the value of resistance, the amount of current is being reduced. As you can see that the blue color diagram shows you for the resistance which is less, and this grey diagram shows you for the resistance which is higher. So, for greater resistance, the amount of current obtained is lower, okay. Next thing states that for the source applied Vm is equal to 100 volts, omega naught for this case would be equal to nothing but, so we will just do 1 upon root LC, correct. Root LC value obtained is nothing but equal to 10 to the power 6 radians per second. So, if it is 10 to the power 6 radians per second, we see that the current amplitude is maximum at the resonant frequency. So, you can see quite clearly that the value or the peak obtained for the current is maximum. So, these are nothing but different values of omega, correct. So, for each value of omega you are getting some value of current, correct, but the maximum value of current, is being obtained at nothing but equal to omega naught. So, this is the basic concept of resonant frequency, okay. So, that thing being said, as you can see it is in 10 to the power 6 m radians is given to you, okay. So, we see that the current amplitude is maximum at the resonant frequency. Now, since Im is equal to Vm upon capital R at resonance, the current amplitude for case 1 is twice as that for case 2. Why? Because this is for 100 ohms and this is for 200 ohms. So, it is divided by 2 here, okay. So, I think this is the only concept required to be understood. Yes, now we can understand some examples or applications of resonance. So, till now what we understood regarding resonance, first of all we understood that there will be a value of resonant frequency being obtained which can be denoted by omega naught, or we can say that this value of omega naught is nothing but close to or equal to, when it is close to natural frequency, the resonance phenomena occurs, and when resonance phenomena occurs, then the value of current amplitude being obtained is maximum, okay. So, this is the basic concept of resonance. We try to understand it first of all theoretically also, and then we try to understand it mathematically also, what is the value actually being obtained, okay. In resonance, the value of Xc is equal to XL for this RLC circuit, or basically for a circuit which involves a resistor, inductor and a capacitor, fine. So, now let us try to understand the application part of this, some of the examples of this. So, resonant circuits have a variety of applications, for example, in the tuning mechanism of a radio or a TV set, okay. So, how it works for a radio is being explained there, I think. So, the antenna of a radio accepts signals from many broadcasting stations. So, you may have heard that there will be 93.5 FM, then there will be 98.5 FM. So, there are different types of megahertz frequencies which are being offered by different broadcasting stations in a radio. Now, what actually happens, how our radio tunes only to a single frequency and rejects all other different frequencies is the basic concept of resonance only being occurring here. Let us try to understand that. So, in radio what happens? So, the antenna of a radio accepts signals from many broadcasting stations. So, let us suppose there are 5 broadcasting stations, let us say 1, 2, so it is 1, 2, 3, 4, 5. Okay. Let us suppose that the amount of omega for all of them are, let us say this is some 100 m radians. Okay. So, this is let us say 200, let us say this is 450, let us say this is some 600 and let us say this is some 780. Okay. Everything is in m radians. Okay. So, I am just writing MR to denote m radians here. Okay. So, let us suppose these are the 5 radio stations, and for our convenience we need to tune to third radio station. What we will do? So, basically what does the radio do? So, the signals picked up in the antenna acts as a source in the tuning circuit of the radio. So, the circuit can be driven at many frequencies, but to hear one particular radio station we tune the radio, as in we try to change the value of frequency of the circuit. How we will change the frequency of the circuit? So, in tuning we vary the capacitance of a capacitor. So, a varying capacitor is being involved in the circuit. We try to change the capacitance value. So, basically we try to change the value of C. Due to this variation in the value of C, what happens? There is a change in the value of 1 upon root LC, there is a change in the value of omega naught. There is a change in the value of omega. When this value comes very close to the value of omega naught or this value, this natural frequency, it resonance happens, and when this resonance happens we try to listen, or we only and only hear the majority part of this third broadcasting station. That is how a radio works. Okay. So, in tuning we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio station received. So, this is the frequency of the radio station received, and we try to change the value of C such that the value of omega naught is very close to 450 mega radians. Okay. Fine. So, that thing being said, next thing is, so when this happens, the amplitude of the current with the frequency of the signal of the particular radio station in the circuit is maximum. So, when the resonant frequency is happening, then the value of current being obtained will be maximum, and the current when it will be maximum for that particular radio station, will get to hear only and only those radio waves of the particular radio station which we are trying to resonate. Okay. So, it is important to note that resonance phenomena is exhibited by a circuit only if both L and C are present in the circuit. It is very important. L and C both have to be implemented here, because let us suppose, for example, the value of omega which we obtained was nothing but equal to 1 upon root LC. Let us suppose L is not there, that means the value of omega naught will come out to be infinite. Or even if C is equal to 0 and there is a value of L, then also the value of omega will come out to be infinite. If the value of omega is coming out to be infinite, there is no way or no sense in which we can try to measure resonance, because every time the natural frequency of the broadcasting station will always have some natural frequency which is finite. If it is having some finite, we cannot equate a finite value with an infinite value. That is why for each and every case scenario, every time for a resonant frequency to work, L and C should always be present. So, this is how we can understand this concept mathematically also. Okay. So, only then do the voltages across the L and C cancel each other, being both out of phase, and the current amplitude is Vm upon capital R, the total source voltage appearing across R. So, RLC circuit is very important for a radio to work. This means that we cannot have resonance in a RL or RC circuit, because in RL C will be equal to 0 and in RC L will be equal to 0. Okay. So, that thing being said, I think that is the end of this slide, and that is the end of this concept of resonance also. In the next part of this lecture, we will understand a new concept, or basically a subtopic of this resonance only, which is called as sharpness of resonance. So, let us try to understand that in the subsequent class, and then we can move on to the next concept, very important concept as far as exams are considered, which is power factor. So, let me stop it here only. Thank you for this lecture. We will meet in the next part in which we will understand sharpness of resonance. So, thank you so much.